Right guys, nice to see you again, and here we're going to be looking at acceleration. Remember we said that with speed it was a scalar quantity and velocity was a vector quantity. Well, acceleration is another physical property that is a vector quantity, and it depends on direction. So you can see here with a variety of videos that we've got here, some of them you may have experienced before and some you may not have, but in all of them it's a measurement of the change in velocity. So if we start off with the good old ride that you go to theme parks, right? The hair raiser is the one that's at Luna Park in Sydney, and with that one there you start off with no motion at all, and then of course they drop it and you start accelerating downwards. So you're starting to increase your speed as you move down and get pulled down by gravity. So you are accelerating in a downward direction. When you're looking at the carousel that you're moving around, or the chair lift, I think the chair ride, where you're going around and around and around, you might be traveling at a constant speed, but your velocity is changing because you're changing your direction. So therefore, if your velocity is changing, you must be accelerating. And we learn more about that type of acceleration in year 11 and 12 physics. But when you turn a corner, you are accelerating. With the car and with the BMX rider, they're turning corners, and so they are accelerating. In fact, the car, and to the BMX rider to a smaller extent, is accelerating not only because they're changing their direction, but they're also changing their magnitude. They're slowing down as they enter the corner, turning the corner, and then speeding up as they go out of the corner. So they're both changing the magnitude of their speed, right, as they go in and out, but they're also changing their direction, and so therefore that's the velocity component. So there's lots of examples of your acceleration in everyday life, not just simply what most people think: if you accelerate you must be getting faster. Well, if you accelerate, then you can have positive and negative acceleration. The positive acceleration is what we normally say, oh, they're accelerating, they're getting faster. But you can also have a deceleration, that is acceleration in the negative direction, where you're slowing down. So let's check this out with a numerical example. So here we have a dragster. This dragster has already started off. We're not starting at an initial velocity of 0 from rest. They've actually started the race. We just started recording when they went past us, and they're going past us at 3 meters per second. Then they accelerated to their top speed, where we recorded it up here at 15 meters per second. So in this instance here, to work out acceleration, we have to take into consideration their change in velocity. So remember, the formula for acceleration is change in velocity divided by change in time. And in this instance, because we're going in a straight line, the change in velocity is not due to direction, it's going to be due to the magnitude of velocity, which is the same as speed. So when we do change in velocity, we've got an initial velocity and a final velocity. So we designate our initial velocity as u. So that means initial velocity. Okay, in this instance, it's not 0, but it could be 0. So if I had this calculator here, at the moment before I drop it, its initial velocity is 0. As soon as I drop it, it starts increasing its velocity in a downward direction and gets faster and accelerates. But at this moment in time, we've got an initial velocity of 3 meters per second. We have a final velocity of 15 meters per second, so we use the letter V to be final velocity. Okay, so we have to calculate its acceleration. So it is the final velocity minus the initial velocity divided by t, the time over which this acceleration occurs. Now we don't have that labeled on the diagram here, but let's put in some values there. Let's say that the time that we were recording this change in speed or change in velocity, let's say the time was 5 seconds. Alright, so let's do some calculations here. Let's change it to blue. Alright, so our final velocity was 15 meters per second. Take away the initial velocity, which is 3 meters per second, and we divide that by the time over which this occurred, which is 5 seconds. So the units up the top is meters per second. The units down the bottom is seconds. So if we go to our calculator now and we go 15 take away 3 divided by 5, we get 2.4. So we get 2.4 meters per second squared. So these are the units for meters per second squared. Okay, now for those physics heads, right, those mathematical people, you know how that happens, and let me just show you how that works out. So we know that the unit up the top is meters per second. Okay, we know that distance. We know that speed is equal to distance divided by time. So that's meters per second, right? And then we're dividing that by time. So what we're really doing is we've got a fraction, meters per second, and we're dividing that fraction by another quantity. And you remember in maths that when you divide a fraction, right, that's the same as timesing by the reciprocal. So instead of going meters per second divided by seconds like that, what we do is we times it by the reciprocal, which is 1 over s. And then it's just a normal cross multiplication, right? So we've got meters and we've got seconds times seconds, which is seconds squared, and there's our acceleration unit. Okay, meters per second squared. So this I've just put in as extra value for your mathematical brain cells, which you need to be fairly good and competent with maths when you do physics, if you choose it in the senior years. And the more you do it, the more it makes sense. So if you've really got an interest for physics, great, right? Pursue it, but remember, like everything that's challenging, it does require hard work. And so we've got our mathematics there to understand how the units work. At the moment, if it's still confusing, just memorize that acceleration is meters per second squared. So just like the quote here that you can see on your screen, which says success is the sum of small efforts, we've got to make sure that we repeat ourselves and constantly challenge our learning. So all the stuff that you've just learned, can you recite some of the key ideas from this video? Can you describe the key ideas from this video? Can you draw diagrams or something to explain what you've just learned to somebody else? So in order to do that, we need to check what you have down in your notes. So do you have detailed notes with diagrams? We're not looking at just writing 1 or 2 sentences. We're making sure we create new pathways to remember your information. So detailed notes, using color to highlight key definitions and terms. You're writing down questions, of course, to yourself or to your teachers. If you come across something that you're not too sure of, make sure you find out what that means. You've got to make your learning meaningful, right? Just like we say in all the study videos. If it doesn't make meaning, you're just repeating words that don't really have much sense to your brain. It's got to make sense. And then, of course, do you have a plan to frequently revise the material? How often are you going to look at this? Have you watched the video that talks about the frequency of study and the memory curve? So think about all of those things after every single video, because we want to make the information go into your brain and make sense so then you can retrieve it anytime, any day. Okay, I'll see you in the next video.